Welcome to Frankly Developing. I'm your host Frank. And did you notice that over the past years, many functional programming elements have been added to object-oriented languages? Why did that happen? And does it mean we have to abandon our principles? This is the start of a new series looking at functional programming, specifically in the context of object-oriented languages. So languages like Java, C#, Python, TypeScript, and the list goes on and on and on. A solid understanding of these foundational aspects of functional programming is crucial to give you access to some of the most powerful tools we have available. Today we get started on these foundations to make sure you understand the differences and applications of functions, methods, lambdas, closures, higher order functions. Stick around to learn what each of these is precisely, how they look like in actual code, and why you should be able to change your code between these different styles. So let's get started with the basics. Simple functions. They're like the building blocks, a piece of code that you can call and execute some code and group it into these individual things that sometimes are called functions. Let's take a look here at the example code, which is from a previous code review video where we did the evaluation of poker hands. If you're interested in that, it doesn't have anything to do with functions, but of course, take a look. Let's see, if you look at the first one here, you notice that it's the class name again. So this is looking like a function, but we don't usually refer to it with this name function because it serves a special purpose. Having the class name and not really a return type here. Oops. There's no return type here. This is just called a constructor because it's helping us construct the objects, obviously. So it's kind of like a function, but we don't usually refer to it like that. And similarly, there are differences in these namings. So apart from the constructor, we have differences here and here that are very dramatic, particularly to object orientation. Functional programming on its own didn't have classes, so there was no distinction between a function inside a class or outside of it, because there was nothing like that. And most modern object-oriented programming languages also have like pretty hard requirement that you do a class body somewhere around, and also don't have the other variant of a global function, but a pretty similar thing, which is usually like this static function thing. And you can call this, of course, a static function or just a function, because we have a better name for the non-static ones. So those functions you cannot just call from anywhere. You need an object of this class hand here in order to be able to call this evaluate function. And that's why we refer to them with a slightly different name. These are the methods of an object of a class. And method versus function is really just the distinction of the static keyword here. So static means you don't need to create an object. You can just call this from anywhere you have access to this public function. It's like a function. Just call it, give it the arguments, and get back the result. Methods, slightly different. And there's something special sometimes in languages like C# here has this thing which is like a property. So it looks almost like a function declaration, but it's not. It's not something that you call usually to evaluate it. So you see this usually in C# with these brackets that take arguments, like no brackets even is necessary to distinguish it from a property. Technically, these things get confused a lot. Like you can do stuff like return something like empty, for example. So something like that is possible to do, and then have actual code being executed when you get or set a property. So it's kind of acting like a function again, but still we usually don't refer to it as one and prefer to consider this just a property, something different from functions. And as we said, we want to learn how to move back and forth between. So if you have an actual function and you want to turn it into a method, what do you have to do? It's super simple in this direction because it's just removing the static and you're good. You moved from function to method. Now you have access to all your class fields. You can just not call it from anywhere anymore. You need the object first. Just simple change here. Of course, you get some suggestion here to make it static again, to turn it into a function again, because that supports the compiler. Because now you don't have to deal with objects and hierarchies and overrides and any of that. It's just now an easy point to, here's the code that you're supposed to run. Object orientation obviously allows us to complicate things a little bit for methods. And if we want to go from a method like this one back to a function, it's not as easy as just writing static. As you see, we get a compile error then, because we can no longer access these local fields from our class or our object here, and that's why you need to do a little bit more in preparation. So before you do that, you need to find out all these fields that you're accessing and add them as parameters to this function. So here we are accessing these cards, which means we need an enumerable of card, and we call it exactly the same, which of course will give us some warnings that this isn't atypical name. Usually you would write this in lowercase, and we also get warnings down here that we're now kind of hiding the other property here, which is a part of the object state of this thing, and we no longer want to access this. But once we're there, we can add the static, and we're fine. Now we can just, of course, rename this in a better way, and then we have multiple enumerations. So maybe you want to turn this into a list, for example, something like that. Now we're rid of all of the warnings, and now we turned a method into a function, and of course we can go back to this one and also get back to using the local field in a similar sense. We can just rename this and then scratch it, and you see in the syntax highlighting the color changes down here on the cards. See that? Now it's white, and now it's back to blue, because now we're accessing the field again. So this is how you move between these very simple building blocks. Before we go into Lambdas, let me know in the comments below if you find these more foundational videos helpful. And please like the video and subscribe to the channel to keep more videos coming. But let's get back to our topic. You probably know and use Lambdas, but where does that name come from? In the 1930s, mathematician Alonzo Church introduced the lambda calculus. It allowed you to define expressions like a variable, a lambda abstraction, which is just a function taking a variable and returning something, and its application, which we would nowadays be referring to as calling the function. The lambda calculus also included alpha conversions and beta reductions. Alpha conversion is a complicated way of saying you can rename the variable. Beta reduction is much more interesting though. It means that in an application you can replace the variable of the lambda abstraction with your calling argument. It's the basis for many more advances in functional programming that came over the years, and follow-up terms like referential transparency or pure functions and many more. But enough history, let's take a look at how this works in modern code. Okay, so let's take a look at this line here. The cards order by. We're just sorting a bunch of cards based on their rank here. And let's ignore the rest of the code for a moment. This inside here is what we refer to as a lambda expression. It's an expression, which means it has a resulting value, and you can write it in different short, concise ways like this in most languages. Sometimes it's equals greater, sometimes it's a minus greater sign, kind of an arrow. And it relates to the lambda calculus, which just says like you have this variable x and you return something. This is just a declaration of a function. It's not actually running anything. And what you can see is like, for example, these days we have the option to also associate this with types. I mean, obviously it's redundant, it already knows it here, but this is a card we got in, and clearly the last almost 100 years we've had some progress on these, and it's not the pure lambda calculus we're working with anymore, but it's based on this. So what else can we do with this? we can take this and actually extract it into a local function and call it maybe getRank or something like that. And you see this is looking more like a traditional function you kind of used to. It takes a card, it returns a rank. And that's really the same thing that we have in here. It's a card that we get as input and returns the rank. So this kind of feels like duplicating it in a sense, and indeed in C# this is called converting it into a method group. And now it looks like this. And notice the big difference here is that in the Lambda expression you have these round brackets that actually means call this thing. Once it gets executed, it's calling the method. Whereas in this method group, you're not having any calls here, no brackets at all, which just means refer to this function. And the call is happening later, of course, when the order by is actually trying to retrieve the ranks for ordering. And you can also, of course, move this onto the class code from the local function to a method. So we just change the name by moving it from one place to another. And similarly, we can make it static in this case. Doesn't make a difference either. Now it becomes an actual function. So lots of variants are possible here. We can go back to inlining it again and having our Lambda expression. And be careful and notice the difference when you extract this part into a local function. You get something else. If we call this getRank, you notice that like we have an actual method call now. So this is doing something completely different than before without these simple brackets. Because this one calls the function and then gets back a function itself, which is the Lambda, again, used as a function. So most languages have a type system encoding also of representing functions like this, and we're getting into a lot of higher order functions here. So let's just get back to the previous version again, and you see back and forth inlining, still kind of different, but also that is more or less the same thing as we had before. So the final thing we could do is we could look into the card and introduce a method like this to getRank. It's definitely not what you would do in C#, so just for demonstration purposes, you could call a method on this card object, of course, in your Lambda. And now it depends on your language. Like Java, for example, has a way to use this and do a similar short syntax where you can refer to something like this without, again, these brackets. C# just doesn't have that, so here you stuck on using it like this. But that's not a huge difference. That's like individual things we call syntactic sugar. Sometimes the language has a few more of these and makes it a little bit more concise and nicer to write. But it's all essentially the same thing. And if you have these things, you can also start from defining the function. So like, okay, I need something that gives me like a rank when I have a card. And then I return the card rank or whatever else I need to calculate. And this is the function that I want to use here. So functions, methods, lambdas, they all relate to each other. And it's super helpful if you can combine these and move back and forth between them, like this, for example. Next, let's take a short look at closures. And first I'll tell you what a closure looks like. So we could have something like a constant here. I'll just put my const. And then inside of our Lambda expression, we could refer to that constant. For example, check if the card rank is greater than my const, and then we want to order it by +1, else by -1, for whatever reason. And since it's an enum, we should take a look at its integer value to do that. So now we have this constant, which, or is it, I wanted to name a little bit differently. And it's not part of the Lambda expression, and this could be anything like a field variable, as well like a local variable, whatever it is. It's not defined inside of this Lambda expression. So if you look at this on its own, it doesn't really define my constant. And that makes a difference if you start doing these translations between these different variants. If you move from your lambda to a method or to a function, etc., then you have to look at, is it still able to access this thing that it needs, or eventually may move it into some argument. So let's see if we, for example, extract this into the local function again. Call it just an order function. Then you see that there's some variable coming into it and it's accessing this constant in there. Of course, inside of here, we could also access the myConst variable, but it's not been declared yet. Now it makes a difference, so I have to do this here before declaring that function. So already you see this dependency on these outside things is impacting your options that you have available on freely moving and changing between these different kinds of functions. So let's get back to inlining that again. And this is like what we refer to as a closure, is when you define this lambda, the implementation underneath in your runtime somehow is no longer a simple function where it just has a bunch of code there and you can call it like a normal function is compiled, for example, or interpreted. This time it needs to have a reference to this outside scope, and that can, depending on your language, become more or less dangerous because this outside scope in languages like C++, for example, might actually go out of memory and be completely cleaned up and removed, and then you have like dangling pointers to it, stuff like that can happen. Or you hold on to some things, even in languages with a garbage collector like Java or C#. If you have a closure like this, that means that there's another object referring to this, in this case myConst, and that means things like the garbage collector can see that there's still reference there, and sometimes you basically get memory leaks from that because the garbage collector cannot clean up due to having these closures still somewhere around. So in compiler details, if you want to write a compiler and go into all the nitty-gritty details, closures can become quite daunting. Practically, it's usually very easy to use. So if you use local lambda expressions, for example, there's typically not a big problem here, particularly if you have simple methods like order by, but the lambda can be garbage collected on its own right after the ordering happened. It's no longer accessible, no longer used. So this typically reduces the risk of any of these things, and most people don't even think about what this closure is and where it comes into play, other than finding it nice that you can access something like the constant inside of these, of course. So higher order functions. That sounds kind of complicated, but don't worry. This video is already getting a bit lengthy. We'll just stick to the practical implication. How do you use this thing? What does it mean for you as a developer? So first, let's get back to the simple lambda. Don't get confused by the closure here. Just have the lambda that says order the card by its rank. Now, everything you need in a programming language to support higher order functions is one simple thing. You need to be able to take a function like this, or like this one, and assign it to a variable. That's it. Once you have that available, you can do higher order function stuff, all sorts of cool things. So if we take this and we extract it to a variable, then you see that this is like an order function now inside of a variable. And how C# does it, similar to most languages, it has like a function kind of type available. Typically you have generic type parameters for the input and output, or numerous inputs if you require something more, for example. Then in this case, since you have a function, what we refer to as higher order. Why is it this higher order? It's because now you have another function here, the order by, and the input of one function is now another function. So a function is in a variable here and gets passed to the other function. And that's really it. So that's all that a higher order function is. But it is the basis for very powerful things we build. So like this ordering, you just have the whole ordering implementation, but you can still define a function, any kind of function, to give it, and then do the ordering by. And then similarly, map and filter, whichever they are called, like in C#, it's called select. It's one of these. That's a higher order function. As you can see on the variant, on the overloads here, there's a func each time that you pass into it. There's a select many, which has a different kind of function that it needs. And we can actually look at what we can do on a whole list or enumerable of cards. And you see that group by is a higher order function, order by, select, the distinct is a higher order function. Like, so many of these are higher order functions. So they literally form the basic building blocks these days of how we work with our programming languages. So many things. Even something simple as a first or default, where you say, pick me the first one, it's actually available as a higher order function. You see there's a simple one that just says, okay, take the first one, but you see there's also overloads here that take a function. And that function basically means you can decide which first you want. So it's just another simple shortcut. You can filter, so like, I want to pick certain cards that satisfy a condition, like only the ace cards, and then I want to check if I get the first or default of that, if I have an ace card or a null. And you already seen the highlight. This just can be simplified by allowing this one in this other place again. And so lots and lots of these methods allow you to write code in a more concise way, in a more generic, parameterized way. Imagine like reaching to an entirely new level. You just not only pass in single values and compute something from it, you can actually pass in the computation itself as a function. And that is so powerful that there are so many other things, and we could keep going on this for a pretty long time. So let me know in the comments if you want to know more about higher order functions and how to use them, make the best out of them. But keep in mind that these should be things you are very familiar with, basic building blocks, because you use them every single day in a modern object-oriented language. So thank you very much for watching, and have fun developing.